Hello, welcome back to Learn Physics. In today's topic, we are discussing about oscillations. Okay, in last video we did tell the spring, what is the time period of a spring, and the motion of a spring also we considered it as a simple harmonic motion. While we are pulling the string and releasing, what will happen? It will oscillate, isn't it? It will be oscillating. The oscillation we considered it as a simple harmonic motion, and we found out the time period also. T equals to pi into root of m by k. Okay, today we are going to study about the simple pendulum. So what is meant by a simple pendulum? Maybe you would have done it in your lab, isn't it? Your lab experiments, you would have done the simple pendulum experiment. So what is the principle behind it? Is simple harmonic motion. So what is a simple pendulum? A rigid support. From a rigid support, a string is there, okay, and a small bob is connected at the end of the string. When we are applying a small force here in this direction and releasing, what will happen? It will be, the bob will be executing harmonic oscillations. That is simple harmonic oscillation it is. Okay, so here the bob will be moving in this manner, and afterwards it will come this direction, it will reach here, and this will be continuing like this. So when it is starting, so from here it is starting its position, means it is going here, coming here, going to this position and going back to this same position. Then it will be completing one oscillation. Going, coming back, then only it will become a one oscillation. Okay, so here we are going to consider about the simple harmonic motion in a simple pendulum. Okay, so here this is the string. Here what are the forces which is acting on the string? Here mg will be acting downwards, and T, tension, will be acting in this direction. So we can divide this mg into components. One is like this and one along this direction. So if this is theta, this will be component which is nearing to theta as cos component, mg cos theta, and this will be mg sin theta. So here we are getting two force components, isn't it? mg cos theta is there, mg sin theta is there. Which one will be helping to provide this motion of the pendulum or motion of the bob as possible with the help of which force, which component of force? See, we have mg cos theta and mg sin theta. mg cos theta is exactly opposing the tension, isn't it? So this T minus mg cos theta, this is equal to 0. Okay, so net force acting on this point will be 0. So the rotational motion will be effective in the case of using mg sin theta. Okay, so the force acting on it is mg sin theta. Okay, so here we can write it as rotational motion is caused by mg sin theta. Okay, so this is rotation, right? So here, so the force is helping to what is happening? The force is helping the rotation to happen, isn't it? Or rotational motion is possible with the help of this force. So what will be the rotational force? That is torque. Torque equals R cross F, R F sin theta, theta and this is perpendicular to each other. So we can find it as R F. Sin 90. Sin 90 is what? What is R here? This is the distance from the point of support, isn't it? From the hinges. Distance from the hinges is, if L is the length of the pendulum, L into, what is the force? F is mg sin theta. Mg sin theta. Okay, this will be opposing force, isn't it? A force is acting in this direction, but we are applying a force in the opposite direction. So minus L mg sine theta. So what is the reason for this negative sign? The restoring torque tends to reduce the angular displacement. Since we are applying a force in this direction, the bob or the pendulum has the tendency to come back, isn't it? So that is restoring torque. Since it is rotational motion, here we will consider it as rotational. See, restoring torque. Restoring torque will be reducing the angular displacement, isn't it? Because of that restoring torque only, that is the bob is coming back, right? So it is reducing the angular displacement. That is the reason we are getting a negative sign over here. Now, Newton's third law. In rotational motion, while we are applying Newton's third law, second law, using second law, what we will be getting? F is equal to ma. Okay, here in the case of rotational motion, while we are applying tau equals I alpha. Okay, so here both are tau, so we can equate I alpha equals L mg sine theta. Thus negative sign is there. So alpha equals L mg divided by I into sine theta. Sine theta, since it is small angles, we can consider sine theta as nearly equal to theta. Or you can write it as sine theta this expansion as theta minus theta cube divided by 3 factorial. See, I'll tell you, sine theta equals theta minus theta cube divided by 3 factorial plus theta to the power 5 plus 5 factorial minus etc. Like that it will go. Higher powers of theta we can neglect. So that is why we are getting it as theta. Or you can say, since theta angular displacement is very small, we can consider sine theta as nearly equal to theta. In that way also you can explain. Okay, so alpha equals minus L mg divided by I theta. Okay, here in the case of SHM, we already got the acceleration as minus omega square x of t. Okay, while we are comparing this one, this is angular acceleration, this is angular displacement. So what is omega here? Omega square is equal to L mg divided by I. Okay, now so root, while we know that, see, I is equal to, for a I is equal to ml square. So while we are substituting that one, you will get it as g L mg divided by ml square. M and m will get cancelled. You will get g by L. Okay, so this is omega square. Okay, what is omega then? So we will get omega as root of g by L. T is equal to 2 pi by omega. Therefore, 2 pi into root L by g. This is the expression for period of oscillation of a simple pendulum. Okay, so period of oscillation of a simple pendulum we are deriving in this manner. So using the rotational effect. Okay, angular displacement only we are considering here. So we are getting t, time period t equals 2 pi into root L by g. Okay, clear how we are finding out the time period of a simple pendulum. So simple pendulum and the motion of a spring, everything we can consider as a simple harmonic motion. And here, when what is the time period of one oscillation? Time period of one oscillation is 2 seconds. Okay, that is seconds pendulum. That and all you would have studied while you are calculating the values. The time period of a seconds pendulum you will find out when L is equal to 1 meter. What is the time period? Isn't it? That is 2 seconds we will get. That is called a seconds pendulum. Okay, so here clear, right? Okay, next we are going to find out what are the restrictions, okay, which is coming, say after when we are releasing the bob from here, and what will happen? It will oscillate. After some time, this oscillation will come to rest position, isn't it? That bob will come to rest position. What is the reason for that? Because see here air or viscous resistance, frictional force, all those things are there, or viscous force will be acting because of the fluid. So all those resistive force or dissipative forces are there. Because of this dissipative force, after some time our bob will come to rest position, or its oscillation is decreasing. It won't be coming back to coming to that much of angle. Angle of separation will be decreasing. It is because of that is called as damping. Okay, that is so. If we are giving a small force and releasing, after some time it will come to rest position, or that is called as damping. Okay, next we are going to study about that damping. Okay, so next is damped SHM. Okay, suppose if I am considering a helical spring, the spring which is with a support, a small mass is here. Okay, I am giving a small force. Because of the restoring force, what will happen? It will oscillate. Okay, after some time we can see it will come to rest position. What is the reason for that? Some frictional force will be acting, air resistance will be acting, some dissipative force are there to reduce the oscillation. Then also it is under simple harmonic motion only, but oscillations are reducing. What is the reason for that? We know that omega equals root of k by m. Okay, force is that equal to minus kx. Restoring force or spring force is equal to minus kx. This and all we know. But because of damping, another force also will be coming to effect, that is damping force. Okay, force due to damping is proportional to velocity. Okay, so we can write it as it is equal to BV. Okay, so what is the total force acting? So it is decreasing, right? So damping also will be decreasing effect. So it is BV we can write. Okay, so what will be the net force acting on it? F will be equal to Fs plus Fd, or we can write minus Kx minus BV. Velocity is with respect to time, x also with respect to time only. So F we can write it as ma. This acceleration in terms of dx and dt, while we are writing it as d square x by dt square. How we are getting this d square x by dt square for acceleration? Because displacement is x. While we are differentiating once, we will get velocity. This velocity, if we are differentiating once more, we will get acceleration. That is, we can differentiate dx by dt once more. So that time you can write it as d square x by dt square only, not dx by dt the whole square. Dx by dt the whole square means it is v square. We are not differentiating, we are taking the square. Okay, so while differentiating once more the velocity term, we will get it as d square x by dt square. So it is d square x by dt square, that is equal to acceleration. Okay, so while we are doing in this way, we will get it as m into d square x by dt square plus kx plus b into dx by dt, that is equal to 0. Or we can write it in an order. Okay, first is square term d square x by dt square, second one is first term dx by dt plus kx, that is equal to 0. While we are solving this one, we will get the value of x as, so if damping is not there, a is equal to this a cos omega t plus phi, like that we will get, right? It is a harmonic motion. Okay, but if the damping is there, we will get the answer as a e to the power minus bt by 2m cos omega dash t plus phi. Okay, so in before damping, if damping is not there, it's only if we are considering only the simple harmonic motion, then our term will be a cos omega t plus phi. isn't it? So here we, after damping, if damping is coming into effect, what we will get, x is equal to a e to the power minus bt by 2m cos omega dash t plus phi. What is that omega dash? Omega dash is the angular frequency when damping is present. Okay, when we are considering damping also, that time instead of omega we will consider omega dash, and the important thing is along with the amplitude we are getting an exponentially reducing term, a e to the power minus bt by 2m. Okay, that is very important. That is, amplitude is exponentially decreasing. So what is the amplitude term over here? This is the amplitude term, right? So it is exponentially decreasing term it is. Okay, amplitude is decreasing. That is what we are seeing here, isn't it? When we are oscillating this one, amplitude is decreasing and finally it is coming to rest position, right? So that is what we showed it through this one. So now how we can find out this? Omega dash equals root of k by m as the actual value which we were getting in the, if we are not considering the damping. Along with that we are getting a damping term, that is root of k by m minus b square by 4m square. That is angular frequency or angular velocity of what is that? Damped harmonic, simple harmonic motion. Okay, so it is decreasing, angular velocity also decreasing with respect to the velocity term. B is the constant which is coming along with the velocity term, right? So it is coming in this way. So how we can write down the energy in the case of a damped simple harmonic motion? See, energy is usually, if damping we are not considering, what is energy? Energy equals half k a square. Right, half k x square or half k a square we can consider. A is the amplitude. Here what is the amplitude? A e to the power minus bt by 2m. So e to the power minus bt by 2m also will be coming. We will take the square. So here we will get it as half k a square e to the power minus bt by m we will get. That means total energy also decreasing exponentially. It will be an exponentially decreasing term as time increases. Okay, if we are drawing a graph, suppose with respect to time how energy is varying, means it will be an exponentially decreasing term like this, exponentially decreasing term. Okay, clear? So this is what about the damped simple harmonic motion. That is, in almost all the practical cases we will be getting with the damping only. We should consider damping, but we don't have in a very sophisticated lab, means okay, we will be having some apparatus to avoid this dissipative forces, but in our labs it is not possible. So we are considering that as a simple pendulum. That is why while you are finding your G value also, if it is not getting exactly like 9.8 also, we will consider that, because we know damping will be coming into effect. Okay, so clear? So next is forced oscillations. What is meant by this? Forced oscillation. So first we learned about the simple harmonic oscillation, then damping is there, we found out. Then next is forced oscillation. What is meant by this forced oscillation? Okay, what is this forced oscillation? See, suppose we are in a swing. We are let's say somebody is pushing us from back, and we are in a swing and we are swinging. Okay, after some time, what if we are not applying any external force through the leg and all? After some time, due to damping, we will come to rest. Okay, but if somebody is there continuously pushing us, means what will happen? That damping won't be affecting, isn't it? That damping won't be affecting to that. That is, see here, spring force along with that normal applied force, a small force is applied. Because of that, one restoring force will be there. But damping also is there in effect. Okay, so to overcome the damping, we are giving an external force, externally driven force. That is forced oscillation. Okay, externally we are applying force. Okay, initially we are giving a small force, then only it will come to that oscillation part. Then after that, when this before to overcome the damping, what we are doing, we are again applying a force. Okay, so here forced oscillation. Okay, how we can write down this one? Yeah, we know that spring force means F is equal to minus kx. Okay, obviously in the case of spring only I am considering, that is easy to consider also. Then due to damping, we know what is the damping force. Due to damping we are getting minus BB, isn't it? Now I am giving a driven force. Okay, external force I am giving. Forced oscillation FO is equal to FO cos omega dt. So this is the applied force. F is equal to F0 cos omega dt. Okay, what is omega d? Omega d is the driven frequency. That is externally we are, once the oscillation started, then also to maintain that oscillation we are giving an applied force. Isn't it? So the total force acting on it is minus kx minus bb plus f0 cos omega d into t. Okay, so while we are solving this one, f plus kx plus bb equals f0 cos omega d t. In the same manner which we did in the last derivation, m into a we can write it as d square x by dt square plus b into dx by dt plus kx equals f0 cos omega dt. So how we will be getting x value here, including this driven frequency. Okay, using that only we will be getting the final equation for x of t. X of t equals a cos omega dt plus phi. Okay, omega d means this will be the x of t, because while we are applying an external force, first external force, due to damping it will be dying out by that time, and after that it is moving only with the help of this angular, the external force or forced oscillation. So x of t will be representing it as a cos omega dt plus phi. So while we are calculating the angular velocity, a equals f0 divided by m square omega square minus omega d square the whole square, omega d square b square the whole power 1 by 2. Like that, one big term we will be getting for finding out the amplitude. Okay, f4, that is amplitude is depending on the initial frequency as well as the driven frequency. Okay, not damping, this is driven frequency, and it depends on the damping also, b. It is depending on damping also. Okay, so here if driving frequency is very much far from the natural frequency, so what will happen if omega d is very much higher than the natural frequency? What will happen to a? A equals f4 divided by, this is a big term, right? So while taking the square, and this will be reducing very much, so we can avoid this one and we will get it as m square omega square minus omega d the whole square root. While we are taking, we will get it as f4 divided by m omega square minus omega d square. But instead of that, if omega d is close to omega, what will happen? See, omega d is very close by, means omega minus omega d will be a very small quantity. So we can avoid this and we will get it as a equals f0 divided by, only this term will be existing, omega d into b square root, raised 1 by 2 is there, right? So we will be getting this as this amplitude. So amplitude we will be getting it for maximum amplitude if omega d is close to omega. That is that position is called as resonance. When omega is very close to omega d, that is when the forced vibration or driven frequency is almost near to the natural frequency, the object will be, symbol motion will be with the maximum amplitude. So when it is moving with maximum amplitude, that position is called as resonance. Okay, clear? So that is the important topics in this. These are the important topics in this in the oscillation chapter. So I think it is clear for you, and next day I will be coming with the chapter waves. Okay, so and one more thing, and if you like the channel, please don't forget to subscribe. Thank you for watching. Bye.